Ladies and gentlemen, to understand how to master deep work, we have to begin by looking at how attention is controlled at a biological and neurological level. Attention is not simply a matter of willpower, it's a function of the brain's architecture and the chemical signals that guide its operation. Specifically, the regulation of attention depends heavily on the prefrontal cortex, the anterior cingulate cortex, and key neuromodulators like dopamine, norepinephrine, and acetylcholine. These are not abstract concepts, they are tangible, measurable systems that dictate whether your brain is in a state of distraction or a state of high-focus engagement. The prefrontal cortex, located right behind the forehead, is responsible for what's called top-down processing. This is the part of your brain that allows you to suppress impulses, plan, and maintain focus on long-term goals rather than short-term gratification. In contrast, bottom-up processing is driven by the limbic system and sensory cortices. It responds to novel stimuli alerts on your phone, sudden noises, or anything that might indicate a potential reward or threat. Deep work requires a shift from bottom-up reactivity to top-down control. That transition is orchestrated by neurochemical changes, most notably through the balance of dopamine and norepinephrine. Dopamine is often mischaracterized as the molecule of pleasure, but in truth, it is the molecule of motivation and salience. When dopamine levels rise in the prefrontal cortex and striatum, the brain tags certain stimuli as worth paying attention to. During deep work, dopamine helps maintain engagement by creating a sense of ongoing reward for sustained effort. Importantly, dopamine release is not constant. It peaks in response to novelty or progress. This is why breaking work into manageable milestones and visually tracking progress can keep attention circuits engaged for longer periods. Norepinephrine, also known as noradrenaline, is released from the locus coeruleus in the brainstem. Its role in attention is tightly linked to arousal. At optimal levels, norepinephrine enhances focus by increasing the signal-to-noise ratio in neural circuits. In simpler terms, it amplifies important signals and suppresses irrelevant ones. Too little norepinephrine and you feel sleepy or disengaged. Too much and you become anxious or hypervigilant. Deep work thrives in the middle of that spectrum where norepinephrine levels are elevated just enough to keep the mind alert and responsive, but not overstimulated. Acetylcholine released from the basal forebrain adds another dimension to focused attention. It sharpens the brain's ability to attend to specific locations or ideas by enhancing synaptic plasticity in relevant neural networks. This means it not only helps you pay attention in the moment, but also supports the consolidation of what you're learning during that time. Practically speaking, this is one reason why states of high focus tend to result in better memory formation and faster learning. Environmental context also plays a large role in modulating these attention systems. Visual clutter, auditory noise, and even social cues can trigger bottom-up attentional shifts. These stimuli activate the salience network and compete with your intended focus. This competition for cognitive resources is not metaphorical. It involves literal changes in which brain areas are activated. When distractions dominate, the default mode network becomes more active, a system associated with mind wandering, self-referential thoughts, and decreased task performance. To reorient toward deep work, the executive control network needs to override this default mode, something that requires deliberate effort and optimal neurochemical support. One of the more recent findings in neuroscience shows that attention is rhythmic rather than continuous. The brain samples the environment in cycles approximately every 200 to 300 milliseconds. During each cycle, the brain decides what to enhance and what to ignore. This pulsatile nature of attention explains why it's so difficult to remain locked in without any lapse. Your brain is constantly shifting between internal and external stimuli, even if only subtly. Mastery of deep work then involves increasing the probability that these attention pulses remain synchronized with the task at hand rather than drifting toward distraction. It's also worth mentioning that attention is a limited resource. The more we fragment it across multiple tasks or digital stimuli, the less of it remains for deep, cognitively demanding work. Each time you switch context from writing to checking your phone or from reading to answering a quick email, your brain undergoes what's called a task set reconfiguration. This isn't just a conceptual switch, it involves a temporary drop in performance and a depletion of cognitive energy as your brain shuts down one neural circuit and activates another over time. This reduces your capacity to engage deeply with any one task, even when you attempt to return to it. These mechanisms aren't just theoretical, they have real-world implications for how we structure our time, our workspaces, and even our internal emotional states. Understanding the neuroscience of attention provides the foundation for building a lifestyle, an environment that supports, not undermines, the pursuit of deep work. To fully master deep work, it is crucial to understand the body's internal cycles, particularly ultradian rhythms, a lesser-known but vital part of human biology that governs periods of heightened focus and fatigue. Unlike circadian rhythms, which operate on a roughly 24-hour cycle and control sleep-wake behavior, ultradian rhythms occur in shorter intervals, typically lasting between 90 and 120 minutes. These rhythms regulate many fundamental biological and psychological functions, including attention, alertness, and even motor performance. In the context of deep work, they serve as the brain's natural architecture for sustained cognitive effort, determining when you are most capable of focusing intensely and when you are most likely to drift toward distraction or fatigue. Ultradian rhythms are governed in part by the interplay between brainstem structures like the reticular activating system, which regulates arousal, and the hypothalamus, which tracks time-related bodily processes. During a 90-minute cycle, the body goes through a predictable oscillation between heightened and diminished levels of alertness. This cycle is mirrored in brainwave activity. In the early part of the cycle, beta waves dominate. These are fast, high-frequency patterns associated with active thought and problem solving. As the cycle progresses, there is a gradual shift toward alpha waves, which are slower and signal a relaxed yet alert state. When the brain slips into theta rhythms toward the end of the cycle, it becomes more prone to daydreaming or mental fatigue. This shift marks a biological signal that the cognitive system needs to reset before entering another period of high-effort thinking. At the neurochemical level, ultradian rhythms are marked by fluctuations in key modulators of cognition and energy. Dopamine, norepinephrine, and acetylcholine levels tend to peak during the early and middle phases of the cycle, supporting goal-directed behavior, motivation, and selective attention. As the cycle nears completion, these neuromodulators decline, while adenosine, a molecule associated with sleep pressure and fatigue, begins to accumulate. This change affects working memory, task accuracy, and even emotional regulation. When individuals ignore these physiological cues by pushing through fatigue with caffeine or digital stimulation, they disrupt the natural wave of neural activation and enter a state of diminishing returns. Not only does performance suffer, but so does long-term focus capacity. Deep work becomes exponentially more effective when aligned with the peaks of ultradian cycles. That means identifying the times of day when your brain enters its natural 90-minute high-performance window and protecting that time, demanding tasks. For most people, the first ultradian peak occurs roughly 90 minutes after waking, provided they've had adequate sleep and early exposure to bright light. This initial window is often the most potent for deep work because cortisol and dopamine levels are naturally elevated, supporting alertness and sustained concentration. The second and third cycles may be slightly diminished in intensity, but can still support deep work if structured properly with rest breaks in between. The decline that follows each ultradian peak is not a sign of weakness or laziness. It is a deeply ingrained biological pattern. Ignoring it creates a cognitive mismatch between what the brain is capable of and what is being demanded of it. The result is a phenomenon sometimes referred to as cognitive drift, the subtle but noticeable loss of precision, memory recall, and creative capacity. To avoid this, the brain must be allowed to downshift. This doesn't necessarily mean taking a nap, although that can be effective for some. Short periods of non-sleep deep rest, Ninstra, mindfulness, light movement, or even brief exposure to nature can reset the ultradian rhythm and prepare the brain for the next cycle of deep work. Interestingly, research shows that elite performers across fields, musicians, athletes, and even chess grandmasters tend to operate in alignment with ultradian rhythms without necessarily knowing the term. Their practice sessions, performances, and rest periods naturally fall into these 90-minute work cycles followed by breaks. This pattern isn't coincidental. It is a reflection of how high performance is tethered to the natural cadence of brain-body synchronization. The same applies to knowledge work. When individuals attempt to grind through long hours without regard to these internal shifts, they tax their attentional systems and disrupt neural plasticity, the very mechanism by which learning and performance are improved over time. From a physiological standpoint, there is also evidence that bodily markers like heart rate variability, HRV, pupil dilation, and even glucose metabolism fluctuate in alignment with ultradian cycles. These aren't just side effects, they are integrated components of a broader system that prepares the brain and body for intense mental effort followed by strategic downregulation. Recognizing these signals can give an individual a tactical edge in designing their day. For example, if focus becomes difficult, it may not be a motivation problem, but rather the natural trough in the ultradian cycle. The solution is not always to push harder, but to step away briefly, allowing the next cycle to begin with full cognitive resources available. By paying attention to when attention is naturally strong and when it wanes, deep work sessions can be scheduled to coincide with peak performance windows, not through force or willpower, but by leveraging the rhythm of biology itself. Cognitive leakage refers to the silent and often invisible drain on mental performance that occurs when the brain is forced to switch between tasks or when it attempts to juggle multiple sources of attention simultaneously. This phenomenon is one of the primary enemies of deep work because it creates a persistent state of divided focus, even when we believe we've returned to the original task. Understanding and eliminating cognitive leakage is essential to sustaining high-level concentration, optimizing working memory, and preventing what can only be described as attentional erosion. At its core, cognitive leakage is not about laziness or lack of effort. It is about inefficiencies in the brain's executive control systems, especially the prefrontal cortex, which is responsible for goal-directed behavior, impulse control, and attentional allocation. Every time you shift your focus from one task to another, checking a notification, glancing at an email, or even thinking about something unrelated, the brain initiates what is known as a task switch. While this may feel instantaneous, the underlying neural mechanisms are far from seamless. Functional MRI studies have shown that task switching requires the brain to deactivate one neural network and activate another, particularly within the parietal system. This shift is metabolically expensive and time-consuming. The delay might be measured in milliseconds, but its cumulative impact is significant. The reactivation of the original task is not perfect either. Some portion of the attentional residue, the remnants of the mental context from the previous task, continues to occupy working memory, reducing the fidelity and efficiency of the task at hand. This residual cost is what constitutes cognitive leakage. From a biochemical perspective, each interruption triggers small surges in stress-related neuromodulators such as cortisol and norepinephrine. These chemicals prime the brain for reactivity, not focused analysis. Over time, repeated micro-distractions recalibrate the brain's default state from focused to scattered. This is further complicated by the role of dopamine, which reinforces behaviors linked to novelty and reward. Each new stimulus, particularly those tied to digital devices, offers a potential dopamine spike. Even if minor, the brain learns to seek these small rewards habitually, making distraction not just a momentary lapse, but a reinforced behavior loop. This feedback loop keeps cognitive leakage alive and well, even when we attempt to return to a task with intention. One of the most deceptive elements of cognitive leakage is that it often masquerades as productivity. Jumping between tabs, responding to messages, and consuming quick bursts of information may create a false sense of momentum. However, this constant low-level mental switching imposes a steady tax on executive functioning. The prefrontal cortex has a limited bandwidth, and when it is required to hold multiple goal states in mind, such as writing a report while keeping track of messages or coding while listening to a podcast, it loses precision. Attention becomes diluted, and the likelihood of errors increases. Even worse, complex reasoning and creative insight, both essential features of deep work, are suppressed in this multitasking environment. The neural networks responsible for these higher-order processes depend on uninterrupted periods of synchronized brain activity, which are incompatible with cognitive leakage. Cognitive leakage is also time-delayed in its effects. You might return to your work and feel that you're back on task, but studies show that full re-engagement with a complex task can take several minutes, even after a short distraction. During this re-entry period, your cognitive performance is compromised. The brain is essentially rebooting the relevant circuits, which can impair memory consolidation, reduce problem-solving capacity, and weaken the mental representations formed during deep learning. This is especially damaging in fields that require intricate reasoning, abstraction, or technical precision. Furthermore, the presence of potential distractions like a phone on the desk or an open browser tab creates a phenomenon known as attentional preloading. The brain allocates a portion of its attentional resources toward monitoring those stimuli, even if they are not actively engaged. This unconscious vigilance contributes to mental fatigue. The attentional system is always scanning the environment for threats or rewards. When devices or platforms are designed to trigger curiosity or anticipation, they become low-grade background noise that siphons away mental energy. This constant cognitive load gradually erodes the capacity for sustained attention. One particularly damaging outcome of persistent cognitive leakage is its long-term effect on attentional habits. Over time, the brain learns to expect frequent shifts in focus. Neural circuits adapt accordingly, making it increasingly difficult to enter and maintain deep work states. This form of attentional fragmentation leads to what some researchers refer to as brain drift, a state in which the mind constantly seeks new stimuli, even in the absence of external prompts. This rewiring reduces baseline cognitive endurance, making the brain less capable of tolerating boredom or resisting distraction, both of which are prerequisites for mastering cognitively demanding tasks. Mitigating cognitive leakage, therefore, requires deliberate environmental and behavioral design. The elimination of multitasking, the reduction of open cognitive loops, and the strategic use of time blocking are not simply productivity hacks, they are ways of protecting the brain's limited cognitive energy from unnecessary depletion. By reducing the number of attention shifts and insulating deep work blocks from interference, it is possible to preserve the integrity of neural performance. When cognitive tasks are siloed with clean boundaries, the prefrontal cortex operates more efficiently, and the brain's natural attentional rhythms are allowed to express their full potential without interference or loss. Controlling internal ante is one of the most underappreciated, yet biologically powerful methods for enhancing focus and sustaining deep work. The internal state refers to the physiological and neurological condition of the body and brain at any given moment, influenced by autonomic nervous system activity, hormonal balance, neuromodulator levels, and sensory input. Deep work does not emerge in a vacuum. It is not simply a matter of intention or discipline. Instead, it is the result of aligning internal physiology with the cognitive demands of the task. This alignment begins with the autonomic nervous system, which includes the sympathetic and parasympathetic branches, both of which play a fundamental role in determining whether the brain is ready to engage with focused effort or shift toward rest, introspection, or even distraction. The sympathetic nervous system is responsible for alertness, action, and readiness. It elevates heart rate, dilates pupils, increases respiratory rate, and releases norepinephrine and epinephrine to prepare the body for immediate task engagement. This system, when activated at a moderate level, is essential for initiating deep work. However, it must be regulated precisely. Too much sympathetic tone in the system tips into stress, agitation, and hypervigilance, all of which impair cognitive control and reduce performance accuracy. Too little, and the system remains in a state of lethargy, unable to generate the neurochemical drive needed to focus. The sweet spot is a state of alert, calm, high enough arousal to promote engagement, but not so high as to trigger fight or flight responses. This optimal zone is sometimes referred to as the ready state, a physiological balance where cognitive resources are fully accessible, yet emotional reactivity is dampened. One of the most reliable tools for shifting into this ready state is controlled breathing. The diaphragm is intimately connected to the vagus nerve, which regulates parasympathetic activity. Slow, deliberate inhales followed by slightly longer exhales stimulate vagal tone, promoting calmness while preserving alertness. Studies show that even just a minute or two of physiological sign, 2 quick nasal inhales followed by a slow exhale can reduce carbon dioxide levels in the blood and shift autonomic balance in favor of focus. These shifts in internal state are not theoretical, they are measurable in changes to heart rate variability, HRV, pupil size, and cortical oscillations, all of which predict improved cognitive performance during demanding tasks. Light exposure is another critical regulator of internal state. Early in the day, exposure to bright blue and rich light stimulates melanopsin-containing cells in the retina. These cells send signals to the suprachiasmatic nucleus (SNN) of the hypothalamus, which regulates circadian and alertness-related processes. This exposure increases cortisol release and boosts dopamine in the prefrontal cortex, both of which enhance wakefulness and improve executive functioning. Individuals who delay light exposure or work in dim environments during the first half of the day experience delayed cortisol rhythms, disrupted sleep-wake cycles, and impaired focus. For deep work to be sustained, especially in the morning, the internal state must be set through strategic light cues that calibrate the body's internal clocks and neurochemical environment. Posture and movement also exert a powerful influence on the internal state. Upright posture with spinal extension increases sympathetic tone and elevates readiness to focus, while slouched or collapsed postures can reduce cortical arousal and make the transition into focused work more difficult. Similarly, light physical movement such as walking or stretching prior to deep work can increase circulation, mobilize energy stores, and elevate dopamine levels. This creates a physiological bridge between bodily activation and mental engagement, priming the system for a seamless transition into cognitive work. Auditory input influences internal state via the reticular activating system, which integrates sound cues into arousal signals. Sounds that are predictable and low in variation, like white noise or known lyrical ambient music, tend to promote sustained attention by dampening external sensory novelty. Conversely, unpredictable or emotionally salient sounds hijack the attentional system, pulling focus toward potential threats or rewards. Choosing the right auditory environment is therefore not just a matter of comfort, it is a lever for tuning internal state toward concentration or distraction. Even silence can be powerful when paired with a ritual of stillness before deep work, signaling to the brain that a transition is underway and that a new focus mode should be activated. Nutrition and hydration further refine internal state. Glucose is the brain's primary energy source, but its availability must be stable to support long bouts of concentration. Large meals or high glycemic foods can lead to blood sugar spikes followed by crashes, creating cycles of hyperarousal followed by fatigue. Stable blood glucose maintained through protein, fats, and low glycemic carbohydrates supports consistent neuromodulator release and reduces irritability and cognitive jittering. Similarly, dehydration, even at levels as low as 1 to 2%, has been shown to reduce attention span, working memory, and executive function. Keeping fluid intake consistent throughout the day maintains cerebral blood flow and supports neurotransmitter synthesis, both of which are essential for maintaining a high-performance internal state. Emotional state is also tightly linked to physiology. Negative affective states such as anxiety, frustration, or rumination engage the default mode network and limbic circuitry, both of which are antagonistic to the task-positive networks required for deep work. Techniques such as brief, not simply about increasing dopamine, but using it strategically to reinforce behaviors that support long-term concentration and cognitive endurance. At a neuroanatomical level, dopamine is synthesized primarily in the ventral tegmental area, vita, and the substantia nigra, and it projects to various brain regions, including the prefrontal cortex, nucleus accumbens, and striatum. These areas are involved in decision-making, reward evaluation, and motor initiation, respectively. The prefrontal cortex, in particular, is crucial for executive function, and its performance is deeply influenced by dopamine levels. However, there is an optimal range. Too little dopamine results in apathy and poor task engagement, while too much can cause impulsivity and distractibility. What matters most in the context of deep work is not just the baseline level of dopamine, but how dopamine pulses in response to actions and achievements over time. Dopamine operates on a reward prediction error model. It increases when there is a positive surprise, when the outcome is better than expected, and it dips when expectations are not met. This means the brain is constantly learning from the gap between expected and actual outcomes, reinforcing behaviors that lead to better than expected results. For deep work, this creates an opportunity to train the brain to associate intense concentration with a steady and predictable internal reward system. This process requires deliberate reward structuring, where the dopamine release is not hijacked by external rewards such as social media, email responses, or instant gratification, but is instead tied to intrinsic milestones, finishing a paragraph, solving a problem, or gaining insight. The key is intermittent reinforcement. Dopamine is more effectively engaged when rewards are not entirely predictable. Structuring deep work sessions with variability, small challenges, time trials, or minor creative constraints can stimulate this reward system without requiring external stimuli. For instance, setting a timer and attempting to beat your own writing or problem-solving speed from the previous session can act as an intermittent reward trigger. Over time, the brain begins to release dopamine not just in response to the completion of a task, but in anticipation of the deep work process itself. This anticipatory dopamine release is what transforms effort into desire and turns discipline into momentum. Crucially, the source of dopamine matters. When dopamine is repeatedly sourced from novelty, quick feedback, or low-effort entertainment, the brain's threshold for stimulation increases. This is known as dopaminergic desensitization, where the receptor systems downregulate in response to overstimulation. As a result, deep work, which offers slower, less immediately gratifying feedback, feels dull or frustrating. To counter this, it becomes necessary to recalibrate the dopamine system. This can be done by reducing the brain's dependency on high-frequency dopaminergic inputs such as endless scrolling, background media, or constant context switching. Just a few days of dopamine minimization, sometimes called a dopamine fast, can restore sensitivity and make the subtler rewards of focused work more perceptible and satisfying. Movement and exercise are also powerful tools for modulating dopamine availability. Physical activity increases the synthesis and receptor sensitivity of dopamine in the brain, particularly in the prefrontal cortex. A short bout of cardiovascular movement before a deep work session, such as brisk walking, jumping rope, or even 5 minutes of dynamic stretching, can dramatically increase the neuromodulatory tone that supports attention and cognitive persistence. This is not merely anecdotal. PT imaging studies show enhanced dopamine receptor availability in individuals following acute aerobic exercise. These biological shifts translate into improved focus, emotional regulation, and task engagement. Another highly strategic use of dopamine is pairing deep work with rituals that predictably stimulate reward pathways. This could be as simple as preparing a specific type of tea before working, listening to a certain ambient sound, or occupying a consistent workspace. These environmental cues eventually become conditioned stimuli, triggering anticipatory dopamine release as soon as the ritual begins. This turns the initiation of deep work into a self-reinforcing behavior. Dopamine begins to pulse even before work starts, increasing motivation and reducing resistance. The process is akin to what behavioral psychologists refer to as cue-based reinforcement, and over time, it creates a neurological association between the workspace or activity and the expectation of fulfillment. Dopamine can also be used retroactively to reinforce deep work. After completing a session, engaging in a deliberate and rewarding action such as brief reflection, journaling a key insight, or stepping outside for sunlight and movement can lock in the dopamine associated with that session. This spike in reward loop teaches the brain that effort leads to a satisfying conclusion, reinforcing the neurochemical architecture needed for habit formation and long-term engagement. Caffeine, commonly used as a productivity enhancer, increases dopamine receptor availability in the brain. However, it should be timed appropriately. When consumed too early or in excessive amounts, it can lead to overstimulation, masking fatigue signals, and driving people to work beyond their natural ultradian limits. A more strategic approach is to delay caffeine intake by 60 to 90 minutes after waking, allowing natural cortisol peaks to occur without interference. This protects the brain's sensitivity to dopamine and avoids the overstimulation crash cycle that impairs later focus. Deliberate recovery is not merely about taking breaks, it's about strategically activating the biological and neurological processes that allow the brain to reset, consolidate information, and re-enter deep work with renewed capacity. Central to this concept is the principle of neuroplasticity, the brain's ability to rewire itself in response to experiences, learning, and repeated effort. However, plasticity is not a passive phenomenon. It is gated by specific neuromodulatory conditions and requires cycles of focused work followed by properly structured recovery. Without deliberate recovery, the neural circuits involved in deep cognitive effort become fatigued, and the brain fails to reinforce or optimize the changes it has begun to establish. The process of neuroplastic change begins during focused effort but is solidified during rest. During a bout of deep work, circuits in the prefrontal cortex and associated attentional networks undergo temporary strengthening. But for these connections to persist beyond the immediate task, they must be stabilized through what's known as synaptic consolidation. This consolidation occurs in large part during rest and sleep when the brain replays recent activity patterns and strengthens or prunes synapses based on relevance and frequency of use. This replay process has been well documented through electrophysiological recordings, showing that hippocampal and cortical neurons fire in patterns during sleep that mirror those seen during learning. Without adequate recovery, these neural signatures decay and learning becomes inefficient or even lost. One of the most effective forms of deliberate recovery is non-sleep deep rest, a state in which the body is deeply relaxed, but the mind remains passively aware. Nstra protocols, which include practices like yoga nidra or specific guided meditations, place the nervous system in a parasympathetic dominant state while allowing the brain to replay and organize recently acquired information. These states are associated with increases in dopamine receptor availability, reductions in cortisol, and enhanced connectivity between the hippocampus and prefrontal cortex, all of which support learning, memory, and future focus. Nstra is especially valuable following intense bouts of cognitive exertion, as it promotes a physiological shift away from sympathetic arousal and toward recovery and integration. Physical movement is another key element in deliberate recovery, particularly low-intensity aerobic exercise. Activities such as walking, cycling, or swimming increase brain-derived neurotrophic factor, BENF, a critical molecule involved in the growth and maintenance of neural pathways. BENF acts as a fertilizer for neurons, supporting the formation of new synapses and protecting existing ones. Engaging in light physical movement after a deep work session not only restores mental clarity through increased cerebral blood flow, but also encourages the biochemical conditions necessary for plasticity. These effects are amplified when combined with exposure to natural environments or sunlight, both of which elevate serotonin and dopamine levels and help recalibrate circadian rhythms that influence alertness and mental energy. Sleep remains the most potent and non-negotiable form of recovery. During slow-wave sleep and rapid eye movement, REM stages, the brain undergoes a variety of plastic changes. Slow-wave sleep is associated with the clearance of metabolic waste from the brain via the glymphatic system and with the stabilization of declarative memories. REM sleep, on the other hand, enhances creative problem-solving and emotional regulation while strengthening procedural and motor memories. Deep work that is not followed by high-quality sleep often leads to diminished recall and cognitive burnout. Sleep also resets neuromodulator systems, particularly dopamine and norepinephrine, restoring the capacity for attention and motivation the following day. Nutrition plays a supporting but essential role in recovery and neuroplasticity. The availability of amino acids such as tryptophan and tyrosine influences the synthesis of key neurotransmitters, while omega-3 fatty acids, antioxidants, and micronutrients provide the raw materials needed for synaptic remodeling and myelination. Strategic timing of meals, such as avoiding heavy food intake right before cognitive work or sleep, helps regulate insulin and cortisol rhythm, which in turn influence the brain's readiness for plastic change and rest. Mental decompression is also a form of recovery that is often overlooked. Time spent in unfocused reflection or quiet contemplation engages the brain's default mode network, DM, which plays a role in processing experiences, forming autobiographical memory, and integrating disparate pieces of information. While the DIM is not conducive to task-oriented focus, it is essential for broad pattern recognition and creative insight. By stepping away from effortful thinking and allowing the mind to wander, ideally in a low-stimulus environment, the brain engages in a kind of background processing that supports later breakthroughs and novel associations. This is why some of the most profound insights arrive during walks, showers, or rest, not because thinking has ceased, but because it has shifted modes. The timing of recovery is just as important as its quality. The brain operates on ultradian cycles of roughly 90 minutes, during which alertness and cognitive resources rise and fall. Pushing through beyond these cycles leads to diminishing returns and increased cognitive errors. Inserting periods of deliberate recovery at the end of an ultradian cycle allows the brain to replenish neurotransmitter levels and restore functional connectivity across networks involved in attention, memory, and decision-making. Over time, these recovery periods not only prevent burnout, but create a rhythm of effort and renewal that supports sustained high performance and accelerates the long-term rewiring of the brain. Ritual design for focus states is a critical yet often neglected component in the science of deep work. While much attention is given to tools, techniques, and time management, it is the deliberate shaping of rituals that primes the brain and body to enter, maintain, and return to deep cognitive states. Rituals are more than just habits. They are structured sequences of behaviors and cues that, when repeated, train the nervous system to associate specific actions with heightened attention and reduced distraction. They establish a neurological preamble, a sort of prelude that prepares the entire system for intense, uninterrupted concentration. The power of rituals lies in their ability to create predictability. The brain thrives on structure, especially when it is preparing to engage in effortful cognitive tasks. A ritual acts as a neural bridge, transitioning the mind from an open and scattered state to a narrow and focused one. This transition involves downregulating activity in the default mode network, which is responsible for mind wandering and self-referential thinking, while upregulating the task-positive network responsible for goal-directed attention. This shift does not happen instantly. It requires a patterned engagement-specific inputs that signal the brain to switch operational modes. One foundational element of a focus ritual is environmental consistency. When a person sits in the same chair at the same desk, in the same lighting conditions each day, the repeated sensory inputs begin to serve as cues. Over time, just walking into that space and sitting down triggers a cascade of neural activity that orients the brain toward focus. This is due to associative learning, where the hippocampus and amygdala help encode the environment as part of the context for deep work. The more consistent the context, the stronger the association becomes. The workspace itself becomes a cognitive anchor. Time of day also plays a crucial role in ritual design. The circadian rhythm and ultradian cycles influence alertness, neuromodulator availability, and even working memory capacity. When deep work is anchored to a consistent time of day, the body's internal clocks begin to anticipate that demand. This anticipatory mechanism can trigger an upregulation of norepinephrine and dopamine, both of which are necessary for sustained attention. A ritual that begins at the same time each day taps into this biological readiness and can significantly reduce the friction required to initiate focus. Physical movement prior to deep work is another powerful element in ritual design. Light exercise, such as a short walk, a few minutes of stretching, or even breath work, helps signal to the nervous system that a state change is about to occur. Movement increases blood flow to the brain, raises dopamine levels, and clears residual stress hormones like cortisol. When this movement is consistently paired with the start of a deep work session, it becomes a trigger. Over time, the brain begins to anticipate focus as a consequence of movement, and this anticipation itself becomes part of the neurochemical pathway toward concentration. Sensory inputs such as sound and scent can be deliberately integrated into rituals to reinforce neural conditioning. Non-distracting background sounds like brown noise, binaural beats, or ambient textures can help mask environmental distractions while also becoming part of the ritual scaffold. Similarly, specific scents such as rosemary, peppermint, or sandalwood, when used consistently, can activate the limbic system and signal that a focus state is being initiated. These sensory anchors, when paired repeatedly with focused work, strengthen the associative links between external inputs and internal states. Another layer of ritual involves behavioral sequencing, what you do in the minutes leading up to focus. This might involve writing out a brief intention for the session, clearing the desk of distractions, or reviewing a to-do list to mentally load the working memory with task-relevant goals. The act of clarifying intent just before diving into work primes the prefrontal cortex and filters incoming stimuli based on relevance. It also reinforces a sense of agency and purpose, both of which are associated with higher dopamine release and greater persistence in cognitively demanding tasks. Even the transition out of a deep work state can be ritualized. When a session ends, logging what was accomplished, stepping outside, or engaging in a reflective pause helps signal closure to the brain. These end-of-work rituals are not just for psychological satisfaction, they support synaptic consolidation by creating a boundary between effort and rest. Over time, these